Again, hello everyone, and welcome to our session, the Privacy Considerations of Production Machine Learning, presented by our guest speaker, Christopher Choquette. Christopher does research in security and privacy within machine learning models, with a focus on adversarial ML, data privacy, deep learning, and collaborative learning. He's currently an AI resident at Google, and before that, he did research at the Vector Institute in Toronto and also at Intel in the Bay Area. He is an avid volunteer, and without further ado, Christopher, please take it away.
Thanks, Juan. Hello, everyone. So I'm just going to share my slides really quickly. Awesome. It's nice to meet you all. And as Juan already said, I'm a researcher right now at Google, focusing on privacy. And the talk today will be on the privacy implications of machine learning in production. So just to go over the agenda really quickly, we'll first go over some background and basics of machine learning and privacy. And then we'll go over various forms of breaching privacy in machine learning and showcase why everyone, those being people that release machine learning models or people that contribute data to them, should care about privacy risks. I will also go over how to protect machine learning models in production from malicious users or adversaries. And we'll also go over a new challenge in privacy in machine learning, which is arising due to a push for more user data rights, which you can think of from GDPR and other related policies. And this challenge is, how do you accommodate requests for users to remove data, or in the context of ML, to unlearn it? Then I'll have some time for questions at the end, and if there's time and interest, we can go over how to collaborate with privacy. So the references are done on each slide for those sections, so you can go back and look at them. So our first setup is that some person or company has collected user data and joined it to create some database. And this person is going to use this data to train a machine learning model. In this context, it'll generally be a deep neural network, which is going to be trained incrementally on the data set using a variant of stochastic gradient descent. And this incremental process will lead to a final model at the end that can be released in production. This situation describes centralized machine learning model training. And the second setup is when data is instead owned by separate parties or users. And in this case, data will be selected from those different clients and brought to a central server to train a central model on the distributed join of this data using a variant of distributed SGD. This situation is the distributed setting, which is rapidly growing in popularity in both research and production because of its privacy benefits. Now I'm going to begin to define a few notions of privacy. In general, privacy aims to answer a few key questions: who gets to see private data, and how queries into large databases reveal information about that data. These questions bring up two different technical definitions for protecting privacy, which are confidentiality and differential privacy. Confidentiality focuses on limiting access to viewing in plain text private data. In general, ensuring confidentiality protects the inputs to a mechanism. And you can think of tools that protect confidentiality as encryption or secret sharing data protocols like oblivious transfer and secret sharing. Differential privacy instead limits what can be inferred about a database through queries into it. In this way, you can think of it as protecting the output of some mechanism, say a machine learning model. In the context of machine learning, you can think of gradient updates as queries into the database, and differential privacy protects how much privacy leakage is incurred through each gradient update. It does this by ensuring that the deviation between similar databases is minimal, or that the outputs don't strongly depend on a particular input. In general, privacy in machine learning is concerned about leaking information about user data or about the model parameters. And there are several different attacks on user data that have been studied here. There are membership inference attacks, which are very well known, and we'll go over those in detail. And assuming you can do membership inference, there are stronger attacks, such as attribute inference or property inference and linkage attacks. Breaching confidentiality is done through model extraction attacks, which are a form of malicious knowledge transfer between the production model and a stolen copy by some adversary. So now we're going to go into more detail about these attacks. Membership inference attacks are one of the simplest forms of privacy leakage and is a good formulation of privacy leakage to study in research. It is really easy to implement and test, making it a great benchmark for privacy leakage in models. The goal of this attack is for a malicious user or adversary to determine if a given data point was a member of the training set. And this is privacy leakage because no one should know which data was used to train a model. This can harm the privacy of an individual in quite a few scenarios because we can deduce extra information about that user. For instance, consider the case where we have a model predicting different drugs for cancer patients based on their morphological data. In a normal circumstance, querying this model on user data doesn't tell us if that person had cancer. However, if we deduce that a data point or a user was in the training set, we learn that they indeed did. So how do we deduce membership? Say a company has acquired some data, and we'll call this the training set. Then all the other data is considered our testing data, which doesn't really need to be data from the same distribution as the training set. It could be as far removed as, say, another similar data set. This company could train a machine learning model in the training set and then release it as a public ML service. Now, an adversary will try to attack this service called our target model. We're going to assume that the adversary has acquired some user data, and what they're going to do is they're going to query this target model on these inputs, obtaining h of x, the confidence vector predictions, which they're going to pass to their trained attack model to label the points as members or not, which are the blue and the orange here. This attack model could be as complex as a deep neural network or as simple as a threshold and can be trained in a few different ways. For example, the adversary could train a source model that mimics the target model using their own data from a similar distribution as the target model's data, or just learn some rule that separates random data from real data. I also want to draw out that until recently, a lot of these attacks require the full confidence vector, or you could think of it as the softmax output of the machine learning model. Membership inference attacks are now getting stronger. For instance, some work that was recently published explores label-only attacks that use only the predicted hard labels rather than the full confidence vector. These attacks issue many label-only queries to analyze the robustness at that data point, as this illustration shows. And in this work, there are 3 different label-only attacks. The data augmentation attack is based off of the idea that models trained with data augmentations can overfit to them. And so 2 common augmentations were evaluated, rotations and shifts. The boundary distance attack leverages the monotonic relationship between a linear model's confidence score, so that's softmax output or binary output, and the distance to the boundary, which is calculated using a label-only adversarial example. Finally, the third attack is a noise attack, which is quite query efficient and looks at the model's accuracy under Gaussian perturbations. If the inputs are binary there, instead, you flip the inputs using a Bernoulli distribution. Starting from membership inference, we can even attain stronger privacy breaches, such as attribute inference. One simple attribute inference attack, which directly uses the membership inference attack, works as follows. Say we start with some partial data record we have for users, so some columns are missing. We're going to impute those missing values, say uniformly. Then what we're going to do is we're going to continue to query membership from some target model. If it's not a member, we'll keep changing and imputing those values, potentially with some knowledge of which of the attributes are likely wrong. And we're going to continue this until we see that the data point is a member. If it is, we conclude that this data point is a member and that those imputed values are the missing values. So we've learned something about those missing columns. Linkage attacks were already common outside of machine learning, but could also be used in ML as follows. Say we have multiple machine learning models trained on different attributes, but overlapping users. We can query a user to each ML model, and if we can determine membership to the different data sets, we can then learn new attributes for those users. We can gather all this information about the users, and with each link, learn more and more about them, potentially enough to, say, fully identify a user if we had no PII to begin with, or personally identifying information. The final set of attacks I'll go over are model extraction attacks or model stealing attacks, and these aim to steal the model parameters of released public models. In this attack, the adversary will learn a new machine learning model that approximates the target. They do this by using the target model as a service to label data points, which they'll then use for training. These approaches can even be done data-free, where the adversary doesn't have labels or data points and instead generates those data. This attack infringes on your model IP and can even enable stronger privacy attacks against user data by improving the performance of, for instance, membership inference attacks. So here's a quick animation depicting the attack. Let's say we have some training data, we train a model on it and release it as a service. The adversary will generate some training data, or have it query the model, obtaining the labels, and they'll combine this data into their own training set, which they'll use to train a machine learning model to mimic the target. This can be done quite effectively, achieving a stolen copy. Now I'll dive into how to defend against these types of privacy breaches. In the first part, we'll explore how to limit private data leakage. So essentially limiting attacks like membership inference attacks and attribute inference attacks. So in this graph to the right, you'll see an evaluation of many different proposed defenses to membership privacy leakage. On the x-axis is the target model test accuracy, which we want to be as high as possible. And on the y-axis, we have the membership inference attack performance, which we want as low as possible. Ideally, we want it below, say, this blue line. These techniques listed on the left give a false sense of security because our label-only attacks find high success above the blue line. In particular, they break previous defenses known as confidence masking defenses that were thought to be robust to membership inference attacks. There are two canonical confidence masking defenses that were evaluated. The first is memguard, which post-processes model predictions. And as you can see, it does no better than not even defending against membership inference. The second is adversarial regularization, which explicitly minimizes this membership leakage in training. But as you can see, it leads to an unfavorable trade-off because the test accuracy rapidly diminishes by the time you successfully defend against the attack. We also explore data augmentation, which I find really interesting because data augmentation is traditionally used to improve a model's test accuracy, which you can see by the dots in the graph. And just for reference, as those dots grow larger, there's more data augmentation applied, or more of the technique applied. And despite this, the attack accuracy also increases, which is because one of the proposed attacks explicitly looks for overfitting in data augmentations. Finally, weak regularization, so you can think of lambda like less than 1, or like the regularization constant less than 1, doesn't protect against privacy leakage either. So looking at what doesn't protect privacy leakage, we'll now look at what does, and what provides specifically a robust guarantee, while giving a trained target model that has good test time performance. Ideally to the right of this line, which gives us a desirable quadrant in the bottom right, that green quadrant. So these are some of the defenses that give a robust guarantee. And in particular, we can see that differential privacy well protects against membership inference attacks, in particular well below that line, but it comes at a huge cost in test accuracy. However, using transfer learning can actually recoup those losses, leading to well-performing test models that are still well defended against privacy leakage. A close second is strong dropout, which has a really good trade-off as well, but falls just outside that green quadrant. And finally, we'll note that strong regularization can also protect against privacy leakage, but similar to differential privacy, comes at a cost in terms of test time performance. And the regularization values here are around the order of 2 to 3 for lambda. And to recap, at least from the results in this paper, the best defense found was differential privacy with transfer learning. For those unfamiliar with differential privacy, I'll give a quick introduction to DPSGD, which is the seminal optimizer for differentially private training. It's a variant of stochastic gradient descent that includes modifications to provide a rigorous DP guarantee. And you can find it in many packages like TensorFlow Privacy, which is available for TensorFlow. The guarantee that DP provides, to recap, can be interpreted as outputs do not strongly depend on inputs, which we'll now formalize. An epsilon DP guarantee says that for all databases differing in only one entry, so say a database with my data and a database without, the mechanism's output, the probability of a particular output will change by less than this multiplicative factor of e to the epsilon. And so for e to the epsilon sufficiently small, what we're saying is that the probability of an output doesn't change if I remove my data. Now I'll go into how DPSGD is implemented. First, what you do is you calculate the gradients per sample in your batch. Then you're going to enforce that each sample has an L2 norm less than some bound, which is C in this image here, which is also known as L2 clipping. Then we're going to aggregate these samples into some sort of group value using a reduction technique. And then we're going to add Gaussian noise proportional to the L2 clipping norm, which will give us some sort of epsilon DP. The more we train, the looser the privacy guarantee will achieve, but obviously the better the model will achieve. And below are just some results from this paper that show that on MNIST, we can actually achieve non-private model performance. Since then, we've done it. But unfortunately, on harder tasks like CIFAR10 and ImageNet, there's still a lot of work to be done to achieve differentially private models that perform as well as non-private models. Now I'll go into the second portion of the defenses, which is protecting against model confidentiality attacks. So one defense that some co-authors of mine worked on was entangled watermarks. And a watermark is similar to watermarks used in digital media, and we're going to put these into deep neural networks, leveraging the fact that a lot of DNNs are over-parameterized. And so what we're going to have is, say, some real task data, and let's say this image of a 3 with label 3, and we're going to say that the adversary also has access to this data. Then what we're going to do is we're going to create some watermarked data. So we're going to take that real task data, say this 3, then we're going to add some trigger to it, which is that square in the bottom right, and we're going to give a new label to that data point. Say it's a 5 now. And the key part here is that the adversary doesn't know what these watermarks are, and so doesn't have access to them. We're going to incorporate this watermark task now into training by training on both the real task and the watermark task, say in alternating steps in training. But so a good thing about this is that the adversary can't remove the watermark task because they're trying to steal it from our model, and also because they don't know about what the watermarks or triggers are. But at the same time, this brings a really intriguing question, which is, will the watermark survive extraction? If they're querying our model on all these data points, but watermarks are outliers, then they might never even learn these watermarks when they extract our model, which is the key reason why we proposed entangled watermarks, which is a form of entangling those watermarks with the real data in training. And how we do this is we're going to leverage the soft nearest neighbor loss, which is this equation here. Essentially, what we're saying is that we want to maximize the distance between the data groups and minimize the distance between the watermarks to the real data. And if we can do this, then what we'll have are watermarks that leverage the same activations as the real data, which we'll see on the next slide. So as I just mentioned, entangling these watermarks with your real data will lead to shared representations. And that will mean that these stolen models will retain the watermarks because on queries with real data, they'll learn that information encoding the watermark as well. And this is an evaluation comparing the two settings. So if we don't use entangled watermarks and we use naive ones, we'll see that the watermark data activates different neurons in the model compared to legitimate data, which means that on queries of normal data, they won't necessarily learn those watermarks. But if we entangle them with legitimate data, you can see that very similar activations are leveraged between the two. This is also just another graphic showing a very similar idea in the representation space of the model. You can see in the before training baseline, in the baseline without entangled watermarks after training, you can see that the watermarks are quite different from the target class. But after training, you can see that they almost perfectly overlap, showing that they're represented quite similarly within the model. Now that we have these watermarks entangled in the model, we're going to look at how we can claim ownership of a particular trained model. And what we'll do is we're going to query models suspected of being stolen, and then we're going to perform statistical tests on the ability for this model to output a weird prediction on this outlier data. And what we found is in the entangled watermarks in particular, with less than 100 queries to a suspected stolen model, we can have 95% confidence that it was stolen or not. And on average, we'll find that using this protocol to entangle watermarks can lead to a less than 1 percentage points difference in the test accuracy of the trained model. But this also raises an interesting question, which is, because watermarks have a performance utility trade-off, can we look at other ways to enable ownership verification just by logging, so incurring no utility degradation of our model? And proof of learning is a relatively new concept that says that we can. It's a permanent record of the effort in training. It leverages an arbitration process by a trusted third party, and it has no utility degradation because it is just a log. And what it is specifically is a log of the weights every so often in training. So let's say we initialize some model with W0 at time steps W1, W2, W3. We'll save the checkpoints of our model in training and so forth. and you can pick checkpointing intervals as desired, explained within the paper. Later, a third party is going to come by and verify that the weights in training make sense. So let's say we're specifically looking at the step between the weights at time step 1 and the weights at time step 2. What this third party is going to do is they're going to take the checkpoint, the saved checkpoint at W1. They're going to perform the update themselves. So logged as well will be the data points used and the optimizer, etc. And they're going to obtain some next state, let's call it W1 prime. Essentially, what we're looking for is that this W1 prime should be equivalent to W2 outside of some delta due to randomness. And what we found is that this is entirely possible to do despite changes in hardware and randomness, and is robust against lots of different spoofing attacks where adversaries might attempt to create a fake spoof. And what this proposed method does is instead of trading off with model utility, it trades off with storage rather than that utility. Cool. And now I'll go into the last portion of the talk, which is enabling unlearning. So we have 3 observations that motivated us to explore machine unlearning. First is that data is distributed in silos or between different parties. It's not centralized anymore, which means that because it's isolated, the model owner might not even have access to it when they want to unlearn this data. The second is that there's a lacking synergy between legal and tech experts right now. So we need clear and provable guarantees that can satisfy even the most stringent requirements that might be imposed. And the third is that there's a complex interplay between data and learned parameters, which means that we can't exactly calculate that entire influence. And this arises because SGD is an incremental process. Those model parameters change over time, which in turn influence what the gradients are for a set of data points. And these observations create a concrete problem in the context of unlearning, which is how do we unlearn data from already trained machine learning models, such as deep neural networks, so that the removal guarantee is easy to comprehend, despite our inability to obtain the exact influence of a data point. So let's define the problem of unlearning. Say we have some data and we train a machine learning model on it. With some randomness, we may learn different models after training, giving us a distribution of possible models. And this arises due to, say, different random seeds, hardware changes, etc. After getting some more data, shown in blue, we're going to train a new model on the aggregate of all this data. Now imagine the owners of this blue data request for unlearning. Our goal is to then unlearn from this model so that the unlearned model is equivalent to what we would have obtained without ever training on that data point in the first place. Because of random reinitialization, our unlearned model may be different. Concretely, what this means is we need the distribution of possible models after unlearning to be equivalent to those randomly initialized and trained without the unlearned data. So there are 2 major solutions that were proposed in prior works. The first is differentially private learning. In this case, we're going to train a model so that its predictions don't strongly depend on the data, and so we don't really need to unlearn data. However, to achieve complete unlearning in this case, we would require that our DP parameter epsilon approach 0, which prevents learning entirely. Regardless of that, differentially private learning always has a strong influence on the accuracy of the model. And also, its guarantee is probabilistic, not a 100% guarantee that that data point is unlearned. The second set of solutions were based off of statistical query learning of Tao et al. And this SQ learning formulation basically just looks at learning as a set of queries into data. However, these solutions only work for simpler models like naive Bayes and don't apply to more complex models like deep neural networks. They can also make a limited number of queries. So both of these solutions don't work for the guarantees that we want to provide. Instead, we propose sharded, isolated, sliced, and aggregated training, also known as CISA. So I'll just go over this really quickly. Imagine we have a large data set D. The first step in CISA is to split this data set into S different shards, resulting in S non-overlapping data sets. Then we're going to train a separate model on each shard in isolation, so the model only ever sees its shard that it's trained on. This reduces its data dependency scope. And then the final step is we're going to aggregate the model outputs of the model predictions like an ensemble, which helps recover the accuracy lost from sharding because it reduces the data size. To further optimize retraining time, we can also introduce slicing in model training, which works as follows. Normally, in each epoch of stochastic gradient descent, we'll pass over the whole data. Instead, we're going to split the data into different slices before training. We'll have R slices. And we're going to incrementally train on more slices as training progresses. So first, we only train on one slice, and then we're going to train on 2 slices, and then 3 and 4. And then say we want to unlearn this red data point. Instead of starting training from the beginning, we can start at that second checkpoint where that data point was introduced, and then start training from that data point, saving us some time. As we'll see, both S and R are tunable parameters that can lead to quite impressive speedups. An S times speedup for the number of shards, and if we have R sufficiently large, an additional 1.5 times speedup. So I'll just show some quick graphs looking at these performances evaluated on a few different data sets. Here we'll see a 3D graph. The bottom left axis is the number of slices, the bottom right, the number of shards, and the top, the speedup. So here we can see that there's a steady improvement as we increase the number of shards. And additionally, slicing can further improve that speedup with just an additional logging and training. But slicing saturates again at that 1.5x speedup. And we evaluated this on lots of different data sets and saw similar results across the board. So that's the main portion of the presentation. Thank you all for listening. My contact details are at the bottom there, and the main takeaways are on the right. So I now welcome any questions if there are any.
Okay. Thank you very much, Christopher, for such a thought-provoking talk. Thank you. So maybe in the meantime, while the attendees take some time to write down their questions, let's begin with a question I have. And I understand this might be proprietary information, so we can just skip the question, no worries. It's about the entangled watermarks. Could you please give us a few more details about their characteristics, like the kind of patterns used to create these watermarks?
For sure. So I'm just going to go back to that slide there. So a key distribution or a key consideration, sorry, when you're creating these entangled watermarks is that you want the triggers added to them to not affect the semantics of the data point. So say here, this is a real data for 3, which we're going to have the label 3 for in this computer vision task. The trigger added, this bottom right square here, is something that doesn't change the semantics. This 3 still looks like a 3, and to any normal model would be predicted as a 3. But because we've specifically added this watermark data, these outlier data points with labels 5, our particular model will be different from every other model in the world and will output a 5 on this watermark data. So when we look to do ownership verification, random models trained on this data won't have this particular weird effect, let's call it, where when I have a white box at the bottom right, my model will output a 5. But my model and any model stolen based off of my model will have this weird output, where on a 3 with a square at the bottom right corner, it'll predict 5 instead of a 3. So those are kind of the considerations you have when creating a watermark in particular.
Okay, thank you. Sounds pretty good. So let's go on with a question from Ronnie. In one of the slides, you mentioned a third party to validate the learning. How will this third party obtain models that are comparable to the original, so as to be generating statistically similar output distributions?
Yes, I believe this is referring to the proof of learning concept. So let me pull that up. There we go. So essentially, the way that proof of learning works is we're going to log a bunch of information throughout training. We're going to log the indices of the data points picked. We're going to log the model optimizer chosen and the loss function. And we're also going to log the checkpoints throughout training. And what this gives us is the ability to recreate a particular checkpoint throughout training. So if the third party wants to validate the step between time step 1 and time step 2, we actually have saved the weights at time step 1. And we also have saved the weights at time step 2. And what the third party is going to ensure is that if I were to take the data points suggested by your saved log, perform the exact same update on starting at this weight 1 that's been saved, that the resulting update, weight 1 prime, let's call it, done by the third party arbitrator is within reasonable deviation from weights 2. And because all of this information is saved in a checkpoint, it's feasible for the arbitrator to do this. But the key challenge here in recreating it is actually that random deviations in different seeds and whatnot can change these results. So we tune this delta to enable for different seeds in different hardware to still lead to the same results, but for other data points or other optimizers or incorrect weights to give a wrong validation at this step.
Okay, thank you. I think we have time for like one more question. It's from Marina. Do you know of any real-world examples where these techniques help in the investigation of leakage of personal identifiable information?
I know that k-anonymity is used in a lot of different setups to help prevent linkage attacks, but actually doesn't work all that well in practice. So differential privacy is a newer formulation that looks at how we can ensure more broadly a robust guarantee against queries on data. And differential privacy is used in a lot of cases within many different companies to ensure that queries into data don't reveal personally identifying information. I'm not too familiar if there are specific cases where these techniques are used a posteriori once there has been a leak to help us recover information, but generally they're used before there's been a leak to prevent them from happening. So they're more of a proactive approach.
Okay, thank you. So I guess in the interest of time, we'll wrap it up for now. I guess like attendees can reach out to you like by email or are there ways they in case they want
For
to
sure,
reach
yeah.
out to you for questions?
I'm just going to pull up this slide again. There we go. Oh, there we go. So feel free to email me. My Twitter handle is also on there, and I'll happily respond to any questions.
Okay, thank you. So for the attendees, please join me in giving Christopher a virtual round of applause. Thank you very much for the talk, and I hope you enjoyed
Thank you
the
very much for
rest of the
having me.
conference.